Today we're going to talk about the wavelength and frequencies in electromagnetic radiation. So we can calculate the wavelength and frequency by using this equation, which is speed of light is equal to the frequency itself divided by the wavelength. So C is the speed of light in the vacuum, which is going to be a constant already. It's going to be 3 times 10 raised to the 8 meters per second. So this is around 300,000. And now we also have F. So F stands for frequency in hertz. So hertz is basically 1 over seconds. And we just flip it over to the numerator. That's why we have hertz. And we also have wavelength, which is going to be in meters. So it's lambda in Greek alphabet. Now let's solve some practice problem. Calculate the wavelength of a photon that has a frequency of 25.5 times 10 raised to the 12 hertz. So that is going to be around billion hertz. Billion hertz, yeah. So we can use this equation. 3 times 10 raised to the 8 is equals to the frequency. That's going to be 2.5 times 10 raised to the 12. And we're going to calculate for the wavelength of this photon. So we can just divide both sides by 2.5 times 10 raised to the 12. So using our calculator, our answer is going to be 1.2 times 10 raised to the negative 4 meters. So this is a little wavelength, meaning it has more frequency and more energy. What is the frequency of a photon that has a wavelength of 1.5 times 10 raised to the negative 8 meters? So we can read that the frequency here is going to be higher because of the equation. If we do solve for the frequency, it's inversely related to the wavelength. So frequency here is going to be higher. So using our calculator, we get a frequency of 2 times 10 raised to the 16 hertz. So as we can see, the frequency here is higher as predicted. What is the frequency of a photon that has a wavelength of 350 nm? So what nm stands for is going to be nanometers. So nano is around times 10 raised to the negative 9. So we can just replace nano with that times the frequency. So we can just divide both sides. What we get here is, so we can find out that the frequency here is a little bit higher because the wavelength is low. So it's around 14. So it is past around billion. Determine the wavelength of if a photon that has a frequency of 95 mHz. So mHz, that's going to be megahertz. So that is a lot of frequency. It's basically around times 10 raised to the 6 is around million. Is it million? Yes, I think it's million. 9 is billion. So we can just basically divide both sides again. So we get the wavelength of 3.1.789. We're going to round this up. So this is the wavelength. What happens to the wavelength of the photon as the frequency increases? So as we look out into our equation, the speed of light times the frequency. So the speed of light here, we have put it up because electromagnetic radiations or electromagnetic waves, they always travel at the speed of light. So that's why it is there. And if we're going to solve for some variable, let's say frequency, it is inversely related to the wavelength. Meaning if the frequency increases, the wavelength will decrease. Also, the reverse is true, that it is going to be if the frequency decreases, then the wavelength is going to increase. So that's inverse proportionality. So that means so we already answered the problem here. So if we want to see the illustration, this is going to be what it's going to look like. So as we can see, the frequency is simultaneous but the wavelength decrease. On the other hand, we have different view if the frequency decrease and the wavelength increase. So here's the wavelength. Look at this distance. It's massive compared to this one. So the answer here is if the frequency increase, then the wavelength will decrease because of inverse proportionality. So let's just write this up. It's just like writing something on your paper. So if the frequency increases, the wavelength decreases. So why is that? Because they are inversely related. And that's it.